what does it indicate? Immediately, if you think it's the lowest energy spectrum, it would be perhaps least invasive or non-invasive for all practical purposes, you can say. But being in the lowest energy end, it is basically a insensitive technique. Now, these are two contradictory things. The advantage is non-invasive, disadvantage is this low energy. This is insensitivity, basically insensitive technique. But then this throws a challenge to the researchers. How to improve the sensitivity then? And that is where the whole technology developed because of that, to achieve the more sensitivity, which means more technological application, and then exploit its being non-invasive, and that is how it went into the brain function and all those studies. So there was a challenge that both these effects should be overcome, but that is the research result of basic research and technology both involved, and the whole fields open for development in this field. Now, rules determining the net, finding out the nucleus, I'll make it a very simple language, finding out a nucleus which is NMR sensitive or NMR non-sensitive. The rules are, if the number of neutrons and protons in the nucleus are both even, the nucleus has no spin and therefore it is non-sensitive to NMR observation. If the number of neutrons plus protons is odd, the nucleus has half integral space. If the number of neutrons and protons are both odd, the nucleus has an integer spin 1, 2, 3 and so on. So a nucleus with spin half or with spin have 2 plus 1 orientation. A nucleus with half spin thus have 2 orientation. In absence of external magnetic field, these orientations are equally probable. If the magnetic field is applied and the energy levels will split, each is given by a magnetic quantum number m. Now, in the ground state, all spins are disordered and there is no energy difference between them, that is, they are degenerate. So, and this shows how they are. So, they are randomly orientated, but once you apply the magnetic field, they get oriented either along the direction of magnetic field or opposite to the direction of magnetic field. There is a small difference in population, very small difference in population between the lower energy state and the higher energy state. And that difference is what leads to what we get the NMR. Now, the difference is very, very small. Let's say at a 400 megahertz NMR frequency, the difference between them is 1.00064. So only the difference is 0.0004064. This surplus population is small when compared to so only the difference is 0.0004064. So now the NMR surplus population is small when compared to applying the specific frequency which shifts them from the lower state. So now the NMR surplus population is small when compared to applying the specific frequency which shifts them from the lower state. So these characteristics are very small and then applying the specific frequency depending upon the lower state. So these characteristics so these are the small and then applying the depending upon the so these characteristics so these are the small and then applying the depending upon so these are the magnetic because the time which they take is related to the condition of the nucleus in the system. Because now the pioneering was related to the condition of the nucleus in the applications in chemistry initially. Now I say this is the pioneering. All the applications of NMR and MRI was observed by Dharmati in the lab of Felix Bloch at Stanford, and they first observed separate lines for chemically different nuclei in the same molecule, a proton rather I should say, and that is, you know, most of you know, is called the chemical shift, which now finds application not only in the chemical structure determination but in all possible MRI actually or all other applications make use of this, or all medical applications make use of it. And which means it can give you, but also